Hey Professor Caps, it's Michael James here with the hydrogen peroxide elephant toothpaste experiment, interactive advanced concept. So what I'm going to do here is I've got my 10% hydrogen peroxide in this measuring cup. What I'm going to do is I'm going to add a couple drops of dish soap into here. Put a little bit in there. Okay. And then I'm going to add some food coloring. We'll go with blue. Just to provide a little bit of visual effect for us. So I got that. And now I'm going to go ahead and mix that solution. Okay. So here's my mixed hydrogen peroxide dish soap. Although I know it's not viscous, it looks like it's pretty viscous. I wonder if that's just the soap floating around in solution. And I went ahead and already mixed our hot water with yeast. What I did is I took about 150 to 200 milliliters of water and put them in a measuring cup, and I stuck it in the microwave for about 45 to 50 seconds. So it was pretty hot when it came out. I assume that the temperature is going to drive this reaction. I can't think of any other reason why we would be heating up the solution. So I've got a clean jar here, which I'm going to use to mix both of my solutions. I'm going to go ahead and put the hydrogen peroxide in first. Now, I wonder if you can see in here. Yeah, you can see the top. Perfect. I was going to do this on a plate, but I didn't want to risk ruining my laptop with a spill. So I'm going to go ahead and mix these two solutions. Oh yeah, there we go. We got some bubbles coming to the top. I wonder if you can see that. So it's not solid. I'm just observing lots of bubbles. The solution's obviously blue. The jar is very warm, and I only added about 150 milliliters of the yeast solution. So I know that temperature of the jar is not directly related. Well, I'm sure it is. That's somewhat influenced by the temperature of the yeast water, but I know that this is in exothermic reaction, which means that it's releasing heat as the reaction proceeds, which is likely why the jar is hot. And I assume that these bubbles would be warm as well. All right, so I'm going to go ahead and move this to the side and explain everything that we just did. So as we saw in the experiment, there was a foam exuding from the top of my glass. Let's see here now that it's kind of finished. See that? Almost looks like a snow cone. So we have the foam that's created from the process of a chemical reaction. The dishwashing soap acts to trap the oxygen bubbles that are being created by the chemical reaction. So hydrogen peroxide consists of hydrogen atoms and oxygen atoms. And under the right conditions, such as in our lab experiment, hydrogen peroxide will undergo the chemical reaction described above to break down into both oxygen and water. Now, that chemical reaction can be described as the following, which is 2H2O2. So two molecules of hydrogen peroxide will break down into 2 molecules of water and 1 molecule of oxygen, or O2. So this is by nature a decomposition reaction because we have the single hydrogen peroxide molecule breaking down into the two smaller molecules. We have the water and the oxygen as the products. And this reaction is also exothermic, which means that it gives off the heat, which I noticed by the glass being warm, and I assume the solution being warm as well. So the catalase in yeast behaves as a catalyst or an enzyme in this reaction, and the catalase speeds up the process of the reaction or the rate of the reaction, which is why the bubbles are forming so quickly. So the catalase in the yeast speeds up the process of breaking down the hydrogen peroxide, which produces oxygen and water more quickly than it would if the catalase was not present. So the oxygen gets trapped by the dishwashing soap as many tiny bubbles. Now, I assume that if we did not use yeast as an enzyme, we would still have the same sort of reaction, although it wouldn't be performed at the same rate that it was under these circumstances. All right, thank you. Have a good week.